Welcome to NanoSurf Masterclass. In this section, we are going to talk a little bit about best practice for spectroscopy. So this is number 7 section. We will have 2 more to go. Next month, we will have the introduction of wave mode. And after that, we will have a special session. So what exactly is force spectroscopy? It's basically one of the basic functions in any AFM. In force spectroscopy, the cantilever is not doing a raster scanning as it is in the imaging mode. Instead, it's doing a raster scan along the z-axis, and during the modulation of the z-axis, the deflection signal of the cantilever is being recorded. So the AFM plot this relation and we call it force curve. So based on these force curves, we can get some information of the nanomechanical properties of our sample. For example, we can get elastic modulus, we can get the adhesion force, we can get information about energy dissipation and indentation. So what's the typical force range measurement of spectroscopy in AFM? It's typically in low piconewton to micronewton, and the elastic modulus range is from 0.1 kilopascal to tens of gigapascal. How do we make sense of this force range? I put a table on the right. It's basically the force required to rupture these intermolecular bonds. For example, it requires more than 1 nanonewton to rupture the covalent bonds. For biotin avidin, it requires like 250 piconewton. For antigen-antibody interaction, it takes 200 piconewton to rupture it. So what we can see in here is that the force resolution of spectroscopy in AFM can cover these ranges. It allows us to study the interaction in single molecular level. So to be more quantitative in our force spectroscopy measurement, some regular experimental pipeline should be followed. First, we need to select a proper probe. So by proper probe, I mean we need to select the proper cantilever spring constant, and we need to decide what kind of tip we are going to use to probe our sample. And then we need to do a high quality calibration of the cantilever. And this section has been covered in our February section. Next, we can perform our spectroscopy on our sample. We need to decide how much force is exerted on the sample, what's the ramping speed and the ramping range, and should there be any pause time when they're in contact, and where exactly should we perform the force spectroscopy. So after all these force curves are being collected, we need to select a proper contact mechanics model that fits our scenario. For example, we can use Hertz, Sneeden, DMT, and JKR model. There are a whole bunch of these contact mechanics model. For choosing the right cantilever, the basic strategy is to select the one that has comparable stiffness to our sample. This table is very useful. We can always come back to check what cantilever is appropriate for our sample. For example, for the neuronal cells, we can probably use the 0.07 range Newton per meter cantilever. If we are doing measurement on a harder sample, for example bones, we can use cantilever for like 40 Newton per meter. So we can always come back to this table to pick the cantilever that is suitable for our sample. So beside the cantilever, the tip shape is also very important. It basically affects which model is eventually being used for the contact mechanics analysis. So there are two types of tips that are commonly used. The first one is a colloidal tip. It's basically a solid sphere adhered to the end of the cantilever. And the other one is just the regular conical tip used for imaging purpose. So the advantage of the colloidal tip is that the shape and contact area is basically well defined. Because this kind of tip, this sphere is actually easier to manufacture, and the dimension of the tip is well defined. So with the colloidal tip, we can have better quantitative data. Also, because the tip is larger than the conical tip, basically we can have less penetration to the sample per se. For the conical tip, the tip radius is in tens of nanometer range, so the tip radius is a little bit difficult to define. Sometimes it will have a smaller indentation depth, but on the contrary, because it has a smaller tip, it will provide better lateral resolution, and it is less affected by the soft extension from the sample if we are doing experiments on the cells. So after we've done our homework to select the proper cantilever and the proper tip, we can move on to do some force curve. Basically, the cantilever starts somewhere away from the sample surface, moving along the z-axis and making contact with the sample. After some set point, the force are being unloaded and we got some adhesion in here. After the maximum adhesion is ruptured, the cantilever goes back to the baseline position. So during the whole process, the deflection of the cantilever is being recorded. So we can see two curves in one figure. One is the forward modulation. It's when the cantilever is approaching to the sample. One is backward modulation. This is when the cantilever is retracting from the surface. If we dissect the force curve into different components, we can actually identify different phases of tip-sample interaction. So in here, A, we have the baseline deflection. There is no deflection in here. The tip is away from the sample. Then in B, in the forward modulation, we will have the snap-in effect, the small kink we see here. And this is typically due to the tip-sample interaction forces. And in C, we have the contact regime of the forward modulation. And after the set point is reached, we can set up some optional pause time to fit our purpose of adhesion study. And then we have D. D is the contact regime for our backward modulation. And in E, we have the maximum adhesion force. After the maximum adhesion force is ruptured, the cantilever is moved back to the baseline. Then it's again away from the sample surface. So for example, if we have some FD curve on the cells on different area of the cell, based on the slope of the contact regime, we can tell that the stiffness of our sample. For example, if the force curves was done on the petri dish, it's basically a straight line. If the force curves were done on the periphery or on the cell center, we can see that the slope is much smaller than that on the petri dish. And based on the slopes, we can know that the petri dish is a lot more harder. than the cell periphery, and it's a little bit harder than the cell center. So besides single point, besides doing force curves on single positions, we can perform force curves in a whole matrix to get this kind of force map. For example, in here we can see the adhesion map and the elastic modulus map. To get these interesting nanomechanical properties such as elastic modulus, indentation, adhesion, we need to extract this information from a force distance curve. But AFM does not directly measure force distance curve per se. It measures the force versus z piezo movement. So it's a FZ curve, but we need FD curve. But the good news is there is a simple conversion. If we assume z piezo movement is z, the tip sample separation is delta, the cantilever deflection is q, then we have the z piezo movement is equal to tip sample separation plus cantilever deflection. If we compare three different scenarios, we can better understand the relation between those parameters. So think about this scenario when the tip is far away from the sample and it's moving towards the cell surface, towards the sample surface. In this phase, there is no deflection of the cantilever, and how much the z piezo moves is equal to the changes of the tip sample separation. If the tip is in contact with an infinitely hot sample, and in this phase, there is no indentation or tip sample separation can be zero, is zero. In this phase, how much the cantilever deflected is equal to how much the z piezo moves. In the third example, the tip is in contact, is indenting a soft sample. So in this scenario, the z piezo movement is the sum of the deflection of the cantilever and the indentation itself. So how do these scenarios look like in the real graph? So basically, if the tip is in contact with an infinitely hot sample, in here, how much the z piezo move is equal to how much the deflection of the cantilever. But in this time, in this graph, it's in voltage. If this is calibrated in nanometers, the slope of this contact regime in FZ curve is 45 degrees. If it's converted to a FD curve, the contact regime is going to be 90 degrees. So we can take advantages of this infinitely hot sample to perform deflection calibration, deflection sensitivity calibration. Because we know the z piezo movement in nanometer, and we also know that z is equal to q on the infinitely hot sample, and we can measure the voltage in the voltage changes in q, so we can calibrate the deflection sensitivity in a unit of nanometer per voltage. So if we are indenting a softer sample in the contact regime of FZ curve or FD curve, the slope is smaller than that on the hard sample. And in an FD curve, it's relatively easy to observe the indentation level of this force curve. So the examples we just talked about are quite simple. In fact, there is tip sample interaction forces should be considered. There are a whole bunch of tip interaction forces when the tip is very close to the sample. One of the major interaction forces is the van der Waals forces. It's basically the dipole-dipole interaction. So it has two parts. One is the attractive part, and the other is the repulsive part. And then we can have a long-range electrostatic force. It can also be attractive or repulsive, depending on the surface charges between the tip and the sample. Then we can have a capillary force. It's basically the force that generated by the thin water layer on the sample when it's measured in air. And of course, we have other forces such as the chemical bonds, chemical forces, or hydration force. So, because the presence of these interaction forces, the cantilever and the sample can be considered as a two spring in a series system. So the top spring is the cantilever itself, and it follows the Hooke's law. And the lower spring is basically the tip sample interaction itself, and its FTS is if FTS is the tip sample interaction force, then the FTS is equal to KTS times the tip sample distance. KTS is similar to Kc in the cantilever, but it's not a constant. We call it force gradient. The KTS per se is a function of D. The two spring in the series system is having some interesting effect on the FD curve. So if we plot a FD curve, the force gradient is basically the slope of this curve. So we can see that it's a function of D. We can also plot the spring constant of the cantilever, and the spring constant is a constant. It does not change with the distance, with the tip sample distance. So we can compare the Kc spring constant of the cantilever and the force gradient along the distance d. From the position A to position D, there is a it's basically in equilibrium. So as the distance decreases, the force gradient is actually increasing gradually. So it's still in balance. And after position D, the force gradient increases dramatically, almost in a sudden. So in this position, the cantilever is not stable because KTS at this position is larger than Kc. So what it does is the cantilever searches for its next equilibrium state. So it jumps from D to B prime in the forward modulation. So this is the so-called snap-in effect or jump to contact. In the backward modulation, when it's at D, the KTS is again larger than the spring constant Kc. So the cantilever is again not stable. So it jumps from D prime to B. And this is the so-called jump, the pull-off effect or jump off contact. In a FZ curve, in the forward modulation, we can observe a sudden change of the cantilever deflection from D to B prime, and in backward modulation, we can see a sudden change of the cantilever deflection from D prime to B. So in this region, the exact force is actually not measured. We cannot determine the force change between D and d prime. So next we can see some examples of force curves that might look a little bit different than a typical one. So in this schematic force curve, we can observe three hysteresis. The first one is we can see a separation between the baselines, between the forward modulation and the backward modulation. So this is typically due to the hydrodynamic drag in the liquid. And in the contact regime, we can also see a difference between the forward and backward curve. And this can be due to the plastic deformation or viscoelastic deformation. And in C, we already know that this is typically due to the adhesion. So we can imply some energy dissipation. We can know something about the energy dissipation in this area in B and C. In this example, the force curves were done in different concentration of potassium chloride. So in low concentration, we can see that there is a long-range repulsive electrostatic force. And as the concentration increases, the repulsive electrostatic force is decreased. At some point, at high concentration, at 100 millimolar concentration, the attractive van der Waals forces become dominant. Specifically, the force gradient of the attractive van der Waals force is greater at this position, greater than the sum of the force gradient of the repulsive electrostatic force and the spring constant of the cantilever. So it's the winner in here. So at this concentration, we can see a snap-in effect. So in these force curves, we can see a wavy baseline with fixed frequency and amplitude. So it's typically due to the laser interference between the lasers reflected from the cantilever back and from the sample surface. So basically, there are two sources of lasers collected at the photodiode detector. So to avoid this, the most effective way is to readjust the laser spot on the cantilever. So beside this, if we are using gold-coated cantilever, it also helps. And if the laser source is SLD, it also helps. So in this example, we can see some features that we have already talked about in our previous slide. First, we can see the baseline separation, and we already know that it's due to the hydrodynamic drag in the liquid. And this drag is actually proportional to the ramping velocity of the cantilever. And it's also related to the viscosity of the liquid. If we look at the figure below, we can see that increasing the ramping speed from 2 micron per meter to 40 micron per meter, we can see the change of the baseline separation. If we are doing the force curves in glycerol, which is a lot more viscous than water, even at the low ramping speed, 0.6 micrometers per second, we can already see a separation. At higher speed, the separation is even larger. So to avoid this, or to reduce the effect of hydrodynamic drag, we can always slow down the ramming speed, or use a buffer that is less viscous. So another feature we can identify in here is the difference between forward and backward in the contact regime. And we already know that this is probably due to the plastic deformation. But beside that, if the open loop is turned on, by that I mean it's not using a closed loop. It can also cause a separation in the contact regime. One more example, one more scenario that can lead to the separation in the contact regime is the tip sliding. For example, if the tip is in contact with an example, or a sample that sample area is not flat, the tip can slide aside the sample and gets away from the initial contact point. When it goes back, when the tip is retracted, it's not going to follow the same path. So that causes the difference in the contact regime. So this example is easy. We can see there is a big wave at the beginning of the force curve. This is typically due to the mechanical vibration. So please do not touch the table. And also remember to turn the active vibration isolation on. And we can also observe some tilting of the baseline. And to avoid this, we can always do the deflection and crosstalk compensation in the software. In the example below, we can see some irregular waviness in the baseline. This huge deviation from the baseline is typically due to the contamination in the liquid. So to avoid this, we can rinse the sample with clean liquid or clean buffer and make sure in the measurement the liquid is clean. If we are doing cell measurement, sometimes if the cell density is too high, they're releasing some floating stuff into the buffer. So in that scenario, we can reduce a little bit about the cell density. It might help. After collecting those force curves, we can finally do our data analysis. The software usually asks you to import the raw data, the force curves, and we also need to provide information of the tip geometry and the Poisson ratio of the sample. And after that, we can select the proper contact mechanics model. We might need to clean up the data if we got some weird looking force curves. If everything works out, we can get those interesting nanomechanical properties. There are quite a lot of models that describes the tip sample interaction. One of the most classic one is the Hertz model in 1881. It describes two solid surfaces interacting with each other. One is a elastic sphere and the other is a flat surface. So it assumes it's a small indentations compared to the sample, and more importantly, the surface adhesion is ignored in this model. So the Sneeden is basically the Hertz model, but instead of a elastic sphere, it's basically a conical tip or pyramidal tip punching on an elastic surface. So in this model, it allows for larger indentation. And the DMT model is basically the Hertz model plus the adhesion outside the contact area. It's suitable for systems with low adhesion and small tip radius. The JKR model is suitable for highly adhesive system, and the adhesion is inside the contact area. And it's for lower stiffness and larger tip radius. So I put a table in here summarizing the equations of Hertz, DMT, and JKR model. The final purpose of this contact mechanics model is to find out the relation between contact radius, the sample deformation, and the adhesion forces. So as we can see in here, the contact radius is proportional to the effective radius and the externally applied force. Is inversely proportional to the total elastic modulus of the system. The total elastic modulus of the system is a function of the Young's modulus of the sample and the Young's modulus of the tip. And this value nu is a constant. It's the Poisson ratio. The effective radius is a function of the tip radius and the sample's radius. So typically the sample radius is a lot more larger than the tip radius. So the effective tip radius can be approximated to the tip radius. So in the indentation, we can see that the indentation is proportional to the externally applied force. It's inversely proportional to the total elastic modulus and the effective radius. Because the Hertz model does not consider adhesion, so the adhesion force term is basically 0. For DMT model, it's basically the Hertz portion plus the adhesion force. So the equation of the DMT model is very similar to the Hertz model. But the JKR model has more terms that includes the adhesion work. So the adhesion situation in the JKR model is a lot more complicated. However, even though it might look very confusing when we went through the equations, in actual operation, for example, in the NanoSurf 8 ANA software, we only need to import our force curves, select the contact mechanics model, provide information about the tip geometry, such as the tip radius, and the software can calculate the mechanical properties of our sample. For offline data analysis, we actually have a few options here. We can definitely use NanoSurf Nano if the data is generated with our instrument. It's very fast and it's convenient to use. We can also use Melton SPIP. It's a very powerful tool. It provides a lot of customization options and filtering function. We can also use the free software Atomic J. Sometimes it's surprisingly good, so feel free to use it. And if we prefer a programming language that offers more degree of freedom, we can also use Python. We have a NanoSurf API in Python, so it's totally up to you. So this is one of the final data presentation after the data analysis was finished. We can always present a topography data and together with the elastic modulus data. And we can also present a histogram of a specific nanomechanics property. If the measurement were done in two distinct areas, for example, they have different adhesion or different elasticity, in the histogram we can identify two independent peaks. So here is another example. It's the polymer foil coated with metal thin film. So in this example, we can see that in the same region, we can compare different nanomechanical properties, and we can analyze how these nanomechanical property correlates with each other and with the topography. So beside the regular way to perform force spectroscopy, we can also use the fluid FM technology. It's basically a system that integrates a pump and a tubing system and a specialized hollow cantilever. It allows us to apply a positive or negative pressure at the open aperture of the cantilever. So for example, we can apply the negative pressure to fix an isolated sphere to the cantilever to create a colloidal tip. We can perform for spectroscopy as usual, and when the experiment is finished, we can apply some positive pressure to release the sphere. Eventually, we can use the same cantilever with different spheres. The advantage of this setup is that we have more degree of freedom on the colloidal tip selection. So the example below is the force map that generated with the fluid FM. So if the fluid FM is combined with the 100 micron Z extension, we can do this kind of mammalian cell pickup experiment. So for example, first we can position the cantilever on the top of our target cell, and we can do the automatic approach. After it's approached, we can apply a negative pressure to fix the cell on the tip of the cantilever, and then the cantilever is retracted from the surface, and during the process the force curve is being recorded. So in this kind of experiment, we can measure the maximum force that is required to isolate a single cell from the substrate. So let's stop the discussion here. Next month, we will have the introduction of wave mode. It is a mode that it is an imaging mode that is powered by photothermal excitation, and it's a off resonance imaging mode. The beauty of this mode is that it allows the topography and nanomechanical property measurement at the same time, and because it's based on photothermal excitation, the ramping speed can be much higher than that of the regular off resonance imaging mode. So please stay tuned, and thank you for your attention.